Good evening, ladies and gentlemen. Welcome to our guests that have joined us for this evening. This is our first ever Photonics100 Meetup. It's lovely to see so many people here for the first time. That we've pored over your entries and your profiles and seen you sort of come into our sphere of knowledge, and it's fantastic to kind of meet you people in person. This is, I hope, the first of many meetups that we'll have. And we hope to sort of deliver some content as part of these. You've enjoyed some round tables this afternoon, and now we're going to have a panel discussion with some Photonics100 alumni and guests. So over the next half an hour, 40 minutes or so, we're going to chat about global challenges in photonics. And I'd like to thank our sponsor, Chroma Technology, for making this afternoon happen. And from Chroma, we have on the far right there, George Derauda from Chroma Technology in Germany. Next to him, we have John Lincoln, who has many hats. He is a Photonics100 alumni himself and is leader of the Photonics UK group. Is that correct? Good enough discussion? Yeah. And then next to me is Chris Dorman from Coherent, who's representing Julie Eng, who is herself a Photonics100 alumni. So this is our panel for this evening. Yeah, you can applaud. Okay, so we're going to talk about a few sort of global challenges. So we're going to start with a question of what do we think is the most important or significant trend in photonics right now? John, can I start with you on this one?
Sure. I think I'm on record on saying a few things. Integration, I think, is the truck that is arriving rapidly, but particularly wafer-based hetero integration, partly because there's a lot of discussion about integration from the semiconductor industry, and they talk about stacking bits of silicon on top of bits of silicon to meet Moore's law. That's fine. Our industry is going to be much more concerned with stacking different materials on top of different materials and how we can get functionality that is not seen before at scale. And the reason I think that's a really interesting trend is because of how it upsets supply chains. We're used to supply chains where we sell components to people, people integrate them into bigger systems. Those bigger systems go to end users who put them in a machine tool or make a mobile phone with them. Heterogeneous integration cuts the middleman out, right? You'll still have those machine tool integrators, but suddenly they will build things on chip at scale that we have never seen before. And the need to buy components may disappear, right, in the traditional form. That's incredibly disruptive. How we do it is one thing, but what it does to supply chains is a completely different impact and may disrupt how we conduct our businesses. And therefore, the people who work this fast will be the leaders of the future. Those who laggard that change may see themselves not existing. So it's a really important trend to see. It's really interesting to see how people adjust to it and where it goes. But disruptive, very definitely.
And George, for you, it's like satellite communication is one of the things you said about this?
Yeah, I would just continue with what John was saying. The one direction is the miniaturization and put components together. And I'm coming from the coating business, so for us it will be an opportunity, but also a challenge to do what we call pattern coating. So right now we have individual filters, and we have a piece of glass we make a coating on, and in the future I see that we need to offer coatings that we can put on structure, silicon wafers, and put a coating on top and on a very small scale. On the other hand, from the biomedical research and diagnostic, I see also a trend to bigger footprints. I mean, everybody's talking about smaller sizes, miniaturization, but if you think about the detector technology that is going to bigger field of view, bigger megapixel sizes, this also requires bigger field of view on the other optics.
And Chris, you were thinking more about sort of long-term trends. What are the long-term trends you see?
So I'm Chris Dorman, work at Coherent, and I'm sitting in for Julie Eng. I hope I do a sterling job of replacing her. She's a CTO of Coherent, and we tend to trade. She's based in California. I'm based in Glasgow, and when something comes up in Europe, I tend to do those, and she covers me when it's a US event. So she's now well immersed in biophotonics, which was kind of my speciality, and I'm learning more about the telecoms parts of our business. So first of all, I would like to say congratulations to the new inductees, the new 100 folk that have been celebrated this week. And then I should explain why I'm going to not answer your question. I'm not going to answer your question because, running a big chunk of a publicly listed company, if I talk about trends, then you can think, oh, that sounds interesting. I might take a view on coherence. So I'm not going to talk about any short-term trends. I'm going to talk about long-term trends. But the 3 long-term trends that I think are quite exciting for the photonics industry are fusion. I think that's now it's in its absolute infancy at the moment, and we're seeing academic publications. But as startups globally start to come to fruition, start to run their first test runs, then I think there's significant scope for a new form of clean energy. And to talk about the other part of our business in terms of its support of the expansion of AI, we can see that data centers are quite energy hungry. So I think fusion's quite an interesting photonics application that we'll see emerging over the next 15, 20 years. I will talk about quantum as well. I think that is intimately interwoven with photonics. I think we use the phrase quantum all the time, but actually quantum and photonics are essentially the same and intimately woven together. And I think there's a lot of opportunity in quantum, as you've probably heard 1,000 times this week and in many other conferences. And the third is the biophotonics, which is kind of where I started in the laser technology in terms of multiphoton microscopy and 3-dimensional imaging of brains, and the understanding of how neurodegenerative diseases progress. I think there's huge advances in that area of science that are exciting to see. And in the same time scales as we'll see quantum computing and fusion, we will see significant advances in the treatment and diagnosis of neurodegenerative diseases.
Okay, thank you. Incidentally, there will be an opportunity to ask questions or add comments towards the end of the evening. We've got a roving mic, so store up your comments and thoughts for them. This is a sort of maybe a slightly different version of the same question. If the first one was about broader trends, this is about technology. So what's the most exciting technology that has emerged recently or that people are working on right now? You can't answer that one.
I can do long term.
Okay. And why is that exciting? So George, maybe start with you. So you talked about PICs a little bit. You talked about miniaturization already.
Yeah. If you ask me about very, very exciting trends from the last, let's say, 2-3 years, I would think on the pandemic we went through and what technology triggered this. And for the biomedical diagnostic market, it was great to have the PCR technology on hands for diagnostics. And if you think about the next coming years, I'm coming back to your first question, I see satellite communication in the near infrared range as a big challenge and could have a good growth.
Okay. What can you say then, Chris, about this?
No, I'll talk about something that's very familiar to everyone, which is the mobile phone technology and the impact that photonics has. So it's very exciting to talk about fusion, quantum computers, potential cures for Alzheimer's, etc. in the future. But I think the one thing that's not really understood about the photonics industry is quite how much it underpins current technology. So if you look at a modern mobile phone, essentially it's a feat of cramming what would have taken a room and then, the size of a PC down into a very small form factor. And that needs miniaturization. And miniaturization has led to a huge raft of photonics technologies that are used in the manufacturing of modern mobile phones. So Where I've touched that in previous roles is the use of ultrafast lasers to cut around the OLED screens. So an OLED screen is essentially layers of plastic, and that doesn't react well to heating, which is your typical CW laser technology. You have to use ultrafast lasers that deliver all of their energy in picoseconds or femtoseconds to effectively disappear this material, take it right. It's not melting. It's essentially not turning to a gas. It's ripping the molecules apart. And so that was part of my career in the past, was developing lasers to do that. That's just one of the process steps in manufacturing a mobile phone. But if you think of all the lithography and the inspection that has to happen on the chips, these are photonic technologies. All of the packaging, given the form factor and the need to put so many components inside of photonics technologies, there are at least 50 laser processing steps in manufacturing a modern mobile phone. If you want to understand a sort of miraculous manufacturing process, then just go and look at how modern mobile phones are manufactured, and almost every single process step is the photonics or laser technology all the way through. And more recently, I've got responsibility for a facility in Göttingen in Germany, and they make excimer lasers that run the annealing step on the manufacturing of OLEDs. That's very exciting. It's very exciting to be part of that ecosystem and to understand how that process step works. And looking forward, they're developing systems for micro LED technology, which is yet another type of display technology. So what I would say is that though my first question might have given the impression that long-term photonics is going to become a very important industry, actually, if you look at the most complex manufacturing process of manufacturing all the components of a modern smartphone, actually photonics is big and dominant in that space already. It's just kind of, as with many photonics technologies, kind of hidden in the background. And I think you did a report on that a few years back.
Hidden economic engine, yes.
The hidden economic engine. So I think that's for the community of photonics, both in the UK and globally, to explain to policymakers and to funding agencies the importance of photonics and how it's kind of hidden in the background behind all of this modern technology we have is pretty important. It's a big industry now. It's an important industry. It's just kind of hidden in the background. So that's a good perspective to take.
Yeah, fantastic. And then John, in answer to this question, you talked a little bit about sort of machine learning in laser processing.
Yeah. So what I think is interesting is picking up on what Chris is saying and what David said here is lasers are ubiquitous in very large-scale manufacturing processes, like making mobile phones. When you make a product in units of millions, tens of millions. And to make that happen, people do hours of applications engineering to fine-tune the process to exactly how the laser works with this material. And you can do that because the volumes are huge. I think what becomes fascinating is then how do we make that more generally applicable to things we are not making in such large volumes? And this is where machine learning and AI in process development becomes really important. Because if you're running the process at a lower volume, you can't afford the sort of levels of application engineering and bespoke development that takes. But if the machine learns how to process the material part pair in real time, you don't need to do that. You don't actually need to know what the optimization process is. You let the machine work it out. And it may only then run for 1,000 cycles, and then it may go and optimize around something new. So the use of machine learning to optimize processes that we take for granted in photonics, they're currently optimized by experts by hand, I think is fascinating. Because you go to the coatings you're talking about. If the machine can learn to do the coating without you having to get the coating designer to do it, the coating designer may not be happy, but then you can run shorter volume runs at the same efficiency as the huge volume stuff. That gets you to more applications, it gets you to more solutions, and it enables us to deliver the sort of customized solutions that really make a difference to the world. And whether it's customized medical, customized device, or a phone that actually meets my peculiar interests of my hand size as opposed to somebody else's hand size. Why not do that? But that's where the machine learning comes in. It is expensive, and we should not forget how expensive machine learning is in terms of the energy resource that Chris says. And ultimately, I think this will be one of the problems about the adoption of AI and machine learning. Somebody's going to work out what the power bill is, and it's not cheap.
Yeah, very, very true. So George, just coming back to you about your earlier comment about miniaturization and PICs, and I asked you about whether what applications will benefit from this new technology, and you talked a little bit about POCT technologies. Do you want to maybe explain a bit about what you meant by that?
Well, I think the miniaturization, and I mean, like Chris was saying that quantum is a keyword and PIC is a keyword, and it has different aspects and different technologies and different stages of how to make it. But what is the beneficial outcome from this shrinking of the components is clearly for the medical diagnostic market. I mean, we just heard from Chris about cell phone technology is shrinking everything, and for the medical diagnostic it's the same thing. So you can do a part of your diagnostic on your own. You have your wearable on your wrist, and also in doctors' offices you can do a lot of diagnostic that needed bigger clinical areas in the past. And also thinking about developing countries and countryside where you don't have access to clinical areas, which also means that it has to be very rugged.
Sure. Okay, I'd like to move on to something that has affected a lot of people in the last few years, but maybe we've come to the end of it, and this is really what the question's about, which is about the supply chain problems. You know, are we through that now? Are there still are there things we've learnt from the last few years? Are there still remnants of supply chain problems? John, let's start with you on this one.
I think it's interesting. Chris will have a hard time answering this question. You shouldn't ask this question, Chris. It's really unfair, right? Because he can't say anything.
I'll just answer a different question.
Yeah, just answer a different question. I think if you talk to people, you go, can they now get the components they need to make their products? Yes. Right? So they're no longer the shortages we once saw. Have some components, for some reason, now got longer lead times than they ever used to have in the past? Yes. Why? Nobody quite understands why something you used to be able to get in 6 weeks now takes you 12 weeks to get, but it's become normalized. So in some cases, a supply chain disruption has now become supply chain normalization, right? And partly that's to do with actually shortage of people, right? So there aren't as many people running things in as many shifts. Partly it's to do with the economics of, actually we're just trying to rationalize the product mix on our production line. So it's going to take you 12 weeks because the slot at which we're going to make that product in is 11 weeks. It's not to do with the fact there's a shortage. But I think what is happening in the supply chain that we can see is a lot more focus on where does stuff come from, right? And this interrogation down through the supply chain that's not just where is my supplier based, but where is my supplier's supplier based? Where's my supplier's supplier based? And where does the material come from that supplier uses? All the way down so that you have that visibility. People aren't necessarily saying you must change, but they are saying you must have visibility down through your supply chain. Now, that's hard, right? Because you might know where you get your coating material from, but where does the guy who makes your coating material get the chemicals from he uses to purify that coating material from, right? And where do they come from? That's quite hard when you drill down through supply chains to even get hold of the information. We've not had to worry about that before. People do now care about that, and they expect that information. And the bigger you are, the more suppliers you have, and that grows exponentially down through the supply chain. That is a data management nightmare, right? At any point you can be asked to say exactly what the national pedigree is of your entire supply chain. Ouch, that's hard work, right? And it's expensive. So people forget that it's an expense. You don't just get to add that stuff for free. It's an overhead.
That's the second time you've used expensive, so this is clearly on your mind today.
Which hotel are you staying?
George, from a vendor perspective, how much of that rings true from a sort of your own supply chain?
I wouldn't answer this from a vendor perspective. I wouldn't rather answered from being part of the supply chain on a very early stage, and the lesson is not 100% made. So yeah, I agree with John that he's saying that people think more about where is it coming from, and maybe I need to have a second source. And but customers were buying supply on a high volume in the 22 and 23 years, and now they're sitting with the parts on the shelf, and going back to the old style, like just on time and lead management, and why they don't ask the question. Just we get the stuff and that's fine.
And Chris, what question can you answer that's related to
I think the next one on your sheet.
Okay. So I want to move a little bit to opportunity now, and where future opportunity is, and where we can talk about geography, we can talk about markets as well. So in terms of geography, China has been sort of a big opportunity and a threat for a while. Is that still the case? Is it moving elsewhere in the world? George, maybe start with you on this one.
I think it's still there. It's opportunity and threat. And while 9-10 years ago, you could make good business in China with the slogan "Made in Germany" or "Made in USA." There's no way to do this these days. So it's all about China first. And on the same side, we see more and more competition from the Chinese market. And if you look outside photonics, you just have to look at automotive. I mean, I'm originally from Germany, so the big car country, and everybody was laughing about Chinese cars 10 years ago, and now who is the biggest competition? The EV vehicles from China.
Yeah, and you also talked about some of the sort of the Far and Near East being growth markets as well. Do you see that sort of a reality, or is that still something in the future?
So which country you are talking?
So like India, Malaysia, Thailand, Vietnam, you mentioned.
Yeah, sure. I mean, India is a big growing market, and it's not easy to understand. And I think many Western companies made a lot of lessons and made the mistakes. But if you are a bit into the country and into the way how business is being a bit special there, then there's a huge potential. And that's the same for the other Asian developing countries, like, as you name it, Malaysia or Thailand, Vietnam. So I see a big potential there.
Okay. Chris, you had a slightly different view on that?
China's both has competitive laser producers, but it's also a huge market. I think if I reflect on what the UK and what Europe is doing in this space, I could talk about OLED manufacturing technology. The OLED fabs, the fabs that make all of the screen technology for your phone, they're all based in China and Korea. And you might think, well, you know, the UK played a big part in developing OLED technology. You know, how come the entire industry has moved to China and Korea? But specifically from the Europeans' perspective, if you were to go through the facilities that are used to manufacture, you know, the huge kilometer-long lines of tools that manufacture things like OLED screens, what you'll find is a significant quantity of that is from Germany and is from Europe, and these exceptionally innovative products, often photonics technology products, are exceptionally well represented from Europe, supporting many jobs. A really high skilled, very highly qualified folk are working in Europe on developing the tools for this technology. So, you know, whilst it looks like the UK, Europe doesn't have a play in this kind of technology and the OLED industry, actually, it has a huge play, and a significant amount of the tools and the photonics technology inside those fabs is developed in Europe. So it's always more complicated than it might initially look. And as I say, it remains a big opportunity, the market in China.
And John, do you want to continue on that?
Yeah, I mean, there are a lot of people in China, right? They buy, by definition, right?
Newsflash, right?
Yeah, newsflash, unknown newsflash. Therefore, they buy a lot of stuff. Therefore, it's a very big market, and they need a lot of tools to supply that market. And I know many people who absolutely say, yeah, China is still a really big opportunity. We can sell a lot of stuff in China. That's not a problem, right? I think the difference is it's now, you've got to think about what you're selling and what difference it's making to your end customer, in the same you would to a customer in Germany or anywhere else. It's a competitive marketplace. Make sure you're offering a differentiated product that competes and provides added value to the customer. And by the way, the customer probably knows what they're doing, especially in terms of process integration, maybe more than some of your domestic customers do. So, as Chris says, look at where the big production lines are. They know what they need, right? And to make those production lines work. I think things like India are really fascinating. Also, newsflash, a few people, right? But a much more interesting and dynamic business environment to work with that a lot of traditional companies have not yet got their head around. A logistics nightmare. Try shipping anything across India. It is really, really hard to move goods around, right? Much harder. They don't have this fancy high-speed rail network or anything else. That it is hard, right? On the other hand, they have an awful lot of talent. And if you look at, say, how they're trending in the world of application of photonics and where they're publishing in photonics, they're growing really quickly. There are a lot of experts in India. Where can we find talent to fill some of the things where we have talent shortages? It's just not a bad place to look. Not a bad place to do design. Not a bad place to think about which aspects of my development function might I do that don't require moving a lot of hardware around, so I don't care about the bad infrastructure, but where I'm moving intellectual value around. India can contribute a great deal to those sort of areas, right? So this is how you don't think about everything as the same. Don't think about, the logistics, I'm just going to run into a logistics nightmare and stop. Think about how you adapt to the local conditions and make use of them, right? And turn them to advantage. That's where these places are really interesting.
Okay. This is your 1 minute warning for your own questions and comments, so be ready to be asked. I just want to finish with maybe some positive outlook from each of you to say, what can we look forward to? We've been through 3 or 4 years of a pandemic, high interest rates, high inflation, supply chain issues. Photonics, as ever, is resilient to those sorts of things in the broadest sense. What can we look forward to, careful, in the next few years that gives hope for photonics as an industry? How can you answer that, Chris?
Well, it's a really easy one to answer, right? So, when was, someone remind me when the laser was invented? 1963? I'm going with one. Okay, I'll go with whatever Miles says. No. It was not an industry at all, and now it's many billions of dollars. So, and I've said this, I've said this, and I think at an earnings call. So I'm fine saying it because I've said it before. But essentially, the laser industry has grown basically monotonically with a few little ripples on it, and continues to grow like that. Photonics technology continues to replace mechanical technology, many other kinds of technologies. So of course, the outlook for photonics is dramatically. I'm dramatically optimistic about it because if you just look at the history since the invention of the laser and photonics technology, it grows and continues to provide new applications. So it will be the fact that whether it's automotive, whether it's your car, whether it's the batteries in your car, whether it's your phone, whether it's the batteries in your phone, the screen, the processor, all of this is underpinned by photonics technology. And so, there's this tailwind for the photonics industry that will continue to be there. Now, who knows? You see, exciting activity in AI, the technologies I've mentioned in quantum and fusion and medical research. These will continue to drive the adoption of photonics technology. So, big picture, without going into the details of what's going to happen next week, photonics continues to grow, and there's a huge tailwind to the industry.
So there's not a problem with photonics demand right now. George, is that something you do agree with?
No, I don't see any problems with demanding. I can now just confirm what Chris is saying. So photonics is more and more the factor in industrial development in the next years, and it will go more and more into different markets.
And John?
Yeah, absolutely. We have got great tailwinds. We are going to continue to grow strongly. I'm fortunate I've seen the numbers of how big the industry has grown in the last year that will be published shortly. And yeah, our industry has got good tailwinds. It will continue to grow strongly. I think one of the really interesting stuff is we've seen lots of growth, and Chris has talked about this, in the application of photonics to manufacturing and making things with photonics. What I'm interested in those mobile phones, how many of the devices inside them are photonics? The screen is a photonics device, the camera is a photonics device. Loads of the thing that measures the distance to your ear to turn off the screen is a photonics device, right? But what we're going to see is an explosion in the photonic widgets as opposed to just the photonic processes. As we get point-of-care devices based on photonics, you get AI processing being done on photonics, in photonics. Those drive a step change in the application and the size and scale and the importance of industry to everyone, right? And I think that's what we will see a lot more of, is electronics is ubiquitous. Photonics is about to become as ubiquitous, if not more so. And that's really exciting, because those aren't linear growths, they are exponential growths, right? And that's fascinating and exciting. Right?
Great, thank you. Any comments or questions on anything you've heard, or either in the roundtables this afternoon, or?
Interrogation by Miles is always slightly risky and dangerous.
No, I'm sure this is all ridiculous. So, as a university researcher, trusted research is incredibly high on our agenda at the moment. How worried do you think we should be about people reverse engineering our products, or your products? They're not my products. Mm-hmm. I get the idea we can sell them the tools. What happens? So what's the thing that stops people reverse engineering these tools?
The most important thing I'll talk about the laser industry in general, is it typically invests 10% of revenue back into R&D. If you stand still, then you've got a problem. You need to be continually innovating to enable the brighter screen, the smaller bezel, the higher pixel density, just to use that particular example. So there's this constant pace of innovation that you need, and the photonics industry does invest rather a lot of money back into R&D, and it's differentiated there in terms of just the pace of innovation. So what I would say is the pace of innovation really is a continuing refresh of the technologies, basically.
And I think I'd add to that, people have been reverse engineering. It's not new, right? What we're only doing is focusing on whether it's happening in one location or another. Reverse engineering is nothing new. People have been doing it for decades. Should we be concerned if it's happening in one location or another? That's a geography question, not is reverse engineering a threat. No, we've innovated our way around it to stay ahead of the people that do reverse engineering. Have we used reverse engineering to educate our engineers and understand what problems are? Yes. In our companies, do we take products in the field that fail and reverse engineer them to understand where failure is? Yes, absolutely we do. So I think actually it's not a new challenge. It's something we've done always to inform ourselves to stay ahead of the innovation curve, right? There's an interesting question about how much we should take our students and say, look at the experiments that failed, right? And don't see them as failures, see them as learning experiences. And how much do we say to our students failure is okay, and the pressure to publish and always push the boundaries and to try and suppress failure as a cultural element is an interesting one, but that's a slightly and subtly different aspect.
Chris, you wanted to come back?
Yeah, I was just sort of reflecting on the question whilst listening to John there. So when I started in the laser industry 2 years ago, it was quite a scientific industry. And I'll just talk about ultrafast lasers specifically because, we're probably both familiar with that. And it would be one scientific laser competing against another scientific laser, and it would be one PhD person working for a laser company versus another PhD working for a laser company. And really, the key elements of that laser were, how long is the pulse, how much energy can you get from it, and the barrier to entry to that particular market is not that very high. If you've got $100,000 and 2 PhD folk that understand how to make an ultrafast laser, we've got another competitor, right? And if you view life through that frame, why not just hire a good PhD person that can build ultrafast lasers? The barriers to entry to this entire industry are quite low. But the evolution that I've seen over my career is that actually it's not, and in those days, femtosecond lasers were not industrial laser systems at all. They were experiments. What's different now is productization, and of course the pulse energy is important, of course the wavelength is important, of course the power level is important, but what's more important for huge fabs which are churning out hundreds of thousands of screens every day, or tens of thousands of battery welds or whatever, is its uptime and reliability. And it's not quite as glamorous for physicists, uptime and reliability, but turning that ultrafast technology into a product took like 10 years. Femtosecond lasers arrive, you can make them. 10, maybe 15 years later, you've got actual products. So when you've got your 3 PhD folk having released this laser with the pulse energies, you typically have spent about 10% of your money developing that product. Most folks that have maybe spent a lot of time in academia will think they've finished. It's like, we've made one, let's just get some more people to make more of them. But it's not like that, because you won't have the reliability or the lifetime, or if the factory goes higher in temperature or lower in temperature, or there's a vibration or whatever, all of this other stuff you need to do. So typically when you've got the pulses and the configuration of the laser that you've got, you're 10% of the way through the journey. When you've done your prototype, you're 10% of the way through your journey, and you've spent 10% of the money. And then the difficult part, there's not many, there's not as much expertise and as many folk that can do it, is turning that innovative laser technology into something that is bulletproof and will last for many years without intervention. Doesn't degrade with time, the beam shape doesn't change, the astigmatism doesn't change, the ellipticity doesn't change, it can withstand vibration, it can withstand temperature cycling, and lots of boring stuff that as a physicist we're probably not that interested in. But I wanted to talk about that in terms of the barrier to reverse engineering, or the barrier to doing it is not the 3 people that can get those kind of pulses out. It's turning that into a robust product that's compatible with a multi-billion-dollar facility that's churning out, millions of X or Y or chips or batteries or screens, basically. And when you understand the expense and complexity of the productization, it kind of puts into perspective the notion of reverse engineering. That's a difficult bit.
A thumbs up there.
Okay. That's the first one Mars has ever given me, by the way.
Time for one more very, very quick question. If there's one at the back.
Those learnings that you have explained to us from the factory floor, those happen in other countries than Europe.
Yep.
So the big factories are set up in Asia, and they experience those learnings, and they improve the products. Are we in a good position in Europe to, in the same way, experience these learnings?
There's an interesting question, right? You can watch something fail, doesn't tell you why it's failed, right? The key bit is understanding why and how you change it, right? So you can use a lot of devices, you can drive a lot of cars. There are a lot of taxi drivers who'll tell you exactly how long you can drive a Mercedes for until it breaks. That does not tell you that they know how to fix the Mercedes, right? That's a different skill, right? So mileage does not translate to knowledge of lifetime, right? Knowledge just means you know when the limit is, right? And that's great for somebody running a big fab. They go, well, yeah, I know exactly how long before it breaks. It's nothing to do with knowing about how you make it last longer. Or, something that might be important, how you make it more adaptable so you can use it on 2 different lines at the same time, or it reflects 2 different ways. It doesn't tell you anything about that, right? It only says about how you know how you use it today. It doesn't say anything else.
So can I just say a few thank yous? So first of all, thank you to our panelists, George, John and Chris. Thanks again to Chroma for sponsoring this afternoon. Thanks to my colleagues Mark, Finn and James for running the round tables earlier this afternoon, and the sterling work by my colleagues Andrew and Rachel in recruiting you all to come along this afternoon. And lastly, thank you for coming along. Enjoy the food and drink.